Okay, let's get going. I should be able to see my screen.
Yeah.
I've already run this notebook a little bit. So to start off with, if you recall, where we kind of ended up with the mini AI framework and single cycle training and stuff was about a score of 90.6, validation score 90.6 with single cycle training, proper initialization, batch norm, and with activation of the ReLU, general ReLU. So we shifted downwards and we also have a slight negative slope rather than 0. So we ended up at about 90.6 and we'll commence our journey there and then try to push it with simple things as far as it can go. So the thing to remember is what our model looks like. It's a very simple convolutional model. It just has 4 convolutional layers taking from 1 to 8 channel, 8 to 16 channels, 16 to 32 channels, 32 to 64. So there are 4. And then at the after we get to 64 channels, when the size is 2 by 2, we go from 64 channels to 10 channel output. That's because we are trying to classify the output into 10 classes or categories, and then we flatten, get rid of this 2 by 2, and then that helps us get to the 64 by 10. We are therefore, since we have 10 outputs, we are able to classify the MNIST images into the 10 classes. So we download it, we then choose the appropriate general value with a leak of 0.1 and a subtraction of 0.4, define the usual metrics callback, the advanced stats callback. We create the callbacks, which are the device callback, the metrics, the progress, and the advanced statistics. And then we also use the initialization, which is we apply the timing initialization with a leak key of 0.1. So the question then becomes, how can we improve on the 90.6? IW is the initialization of the weights. Okay. It's just a partial function of the init weights, and the init weights is a PyTorch function where if you provide a leak key of 0.1, it can kind of adjust and appropriately initialize our networks. According to the timing.
Yeah.
Right, exactly. That's the square root of 2 by number of inputs for every layer. So we were kind of this is just an indication of the code that we use in the get model function. The important thing to recognize, besides what we have already talked about and seen, which is the layers going from NFSI to NFSI plus 1. Activation is whatever we supply. Norm is whatever norm function, batch norm, layer norm. In this case, we use batch norm. And then we return a sequential of these layers, except that after we get to the last layer, which is 64 in our case, because if we don't supply any NFS, which means the list of layers or list of channels, then we take the default to be 1, 8, 16, 32, and 64. And remember, this provides 1, 2, 3, 4 convolutional layers, followed by a flattening, excuse me, followed by 64 to 10, and then flattening. 64 to 10 is a linear network, not a convolution, and then a flattening. So that's what our model default is, and that's what the get model function does. Just keep that in mind because we'll be changing this as we move forward. So one of the things we could try is going deeper. And going deeper means that we increase the number of steps or convolutional that we go through. So we add another set of filters or channels, and we go from 64 to 128. Right? So we have gone deeper, but when we increase the number of channels or filters, that's also called going wider. So this way we are going both deeper because we are adding a layer going from 64 to 128, but we're also increasing the number of filters or channels, and that means going deeper. So this network that we create is both deeper as well as wider. And the way we do that is we first take the first layer, which goes from 1 to 8, and we make it a stride 1. Why is that? Because stride 1, as we know, doesn't change the size of the image, so that when we go from 28 by 28, it remains 28 by 28, and then we are allowed to take the 4 steps to go to the 2 by 2. And instead of going from 64 to 10, we'll now be going from 128 to 10. I guess the only difference in this case. Right, so that's kind of one way that we can try to increase or score. And otherwise we set everything else to be the same and we train. So while that's training, let's kind of try to understand the next step that we are trying to take, which is using that of residual nets. And so what is the concept of residual nets and why are they called residual networks? And how come they do better than traditional convolutional networks? So one of the things that it's all covered in this paper, but the simple explanation, or simplified, I should say, because it's obviously a little more complex than what I'm about to say, but the thing that Cunningham, the same guy who came up with the initialization thing, noticed very early on is that when you just increase the depth of the network from, say, a 20-layer network to a 56-layer network, they found that if we did the same thing as what we do traditionally when we just do repeated convolutions, then we find that the score that's obtained from a 56-layer network is actually worse than that of a 20-layer network. So as you go deeper, you don't get better. And they said, oh, is it the case that just the network fails to generalize better so that if you have a 56-layer network, it's worse than a 20-layer network in terms of generalization, and therefore its validation performance is bad? The answer turned out to be no. It turns out that if we just continue to do convolutions in the traditional way, we find that even training a 56-layer network is worse than that of a 20-layer network. So they found out that the training error rate, as you can see from the plot on the left-hand side of this figure, is still worse for a 56-layer network compared to a 20-layer network. The insight that Cunningham and so on had was to think of the 56-layer network being created with just identity transitions after 20 layers leading up to the 56 layers. And if you think of it that way, that after you do the 20 layers, you just keep propagating don't do convolutions anymore, but just, or even if you do convolution, just make sure that you are propagating the input to the output. If you think of it that way, then there is no inherent reason that the training of a 56-layer network should be worse than that of a 20-layer network. In a sense, the 56-layer network should be a subset of the 20-layer network. If you make 36 layers just be identity layers going from 20 to 36. If that's the case, this delta between training error rate for a 56 layers and 20 layers should disappear. Or in other words, we should be able to between a 56-layer network as well as a 20-layer network. So kind of using that as an insight, the Kevin Hay and co-authors came up with a different way to think of or to connect up the traditional convolutional networks that we see. And this is the network they came up with. So here's the input. Think of the traditional, let's say 20-layer, 56-layer, whatever, as having a single convolutional layer. So you have an input, a single conv layer, and then an output. In the case of this new network that they were coming up with, they said, let's do the following. Let's split the convolution, and we'll see why they do that in a minute. But let's split it into two convolution stages. But here's the thing that we want to do. Take the input and connect it directly, not going through any of these convolutions, to the output. So if we think of it in terms of the equations rather than just the network, what does that tell us? So the output in the output equation for this network is con2 of con1 of in plus in, because the input is also directly sent to the output. So when we come out of this output, what we have is the output coming through the two convolutions, which is the convolution 1 of input and then a convol 2 applied to that output added to the input. So this is the new network that they created. Now, why is it called a residual network? Because if you look at what the convolutional path is actually doing, you can rewrite this equation as out minus in is the combination, or is what the convolutional path is actually trying to generate. So con2 of con1 of in is actually trying to output or mimic the difference or the residual, which is, and a residual is the subtraction of the input from the output. So what's remaining of the output when the input is subtracted from the output, so to speak, is what the convolutional network is trying to generate as its output. Hence the name of these kind of connection, these networks, to be residual network or ResNets. Right. Now, one thing that I've kind of elided or not explained is, or not highlighted, but it should be obvious, is you can only add the input to the output if the number of channels of the output and the input are the same, and the size of the images for the output and the input are the same. In other words, this input can only be added to the two convols of the input, provided that the input and the result of these two convolutions have the same number of filters in the output and the same size of the image. So if that's the case, then we need to ensure that this input path has the same side effectively and results in the same size of the image as what we obtain when we go through these two convolution layers. So what the authors of the paper did is implement a very simple convolution here. In effect, they called this IDCon. It turns out that it's not just simply IDCon, as we'll see in a minute, but it's as simple as it can get. Two-step convolution that enables us to get back or to ensure that the input that's getting added to the output of the two convolution, that the size of this first piece and the second piece, size, when I say size, I mean the size of the image, as well as the number of channels in the image are identical. So let's see how that gets ensured. The first thing we do is we create this two-step convolution. And here it becomes obvious as to why we needed the two steps. So in the first step, we just make sure that we go from Ni to Nf, but we make the stride equal to 1 so that there is no change in the size of the image. And we apply the activation that we have supplied and whatever the norming function is. So the first of the two cons goes from NI input number of filters to output number of filters with a stride of 1, activation, norming, and with a kernel size, whatever we have supplied with, default is 3. Second convolution is where we apply the stride. So the stride could be 2, for example, in which case the shape or the size of the image will change. However, we don't change the filters or the channels. We just keep it the same as NF. So we go from NF to NF with whatever stride is given, and we don't apply any activation. We'll get to the reasons as to why we don't do that in a minute, and we apply whatever norm is given, and the kernel size is whatever kernel size is applied. So two convolutions. The first with a stride 1, and we go from NI to NF. The second with whatever stride is given. The first with the norming and the activation. The second without the activation, but with the norming and a stride and kernel size, whatever we are given. And typically this happens to be a stride 2, but we can have whatever stride is given as input. That's what we will get as a result of applying the two convolution, and we call that a con block. We make it a sequential because of the two. Now, now we create or build out this entire path, which is called, this entire thing is called a rest block. And a rest block looks like this. We just initialize, to NN module, apply the two cons. So self.cons becomes the con block. And now we do the two things which we talked about in this path, going directly from input to output. And what we do there are the two steps. The first is called IDCon, just to keep it simple. In this case, it exists to fix the problem, if you will, if the number of channels Ni is not equal to NF. So if Ni is equal to NF, then on the IDCon path, we don't do anything because we can add, right? So we don't need to apply anything. So sc.loop basically is a no-op. It's from the fastcore library. So if Ni is equal to NF, we apply no-op. If it's not, what do we do? Well, then we apply a con and keep the size the same, because the only thing we're trying to fix is the number of channel delta. So remember, if Ni, this part of applying the con is under the condition where Ni is not equal to NF. So if Ni is not equal to NF, then we make Ni equal to NF by applying a con, and it's a stride 1 with no activation. So we have fixed the situation where the number of filters are different, but we have to be careful because we still haven't fixed the problem where the size could be different. So if, for example, we applied a stride 2 in one of these two cons, then we need to fix that problem. So that is fixed by the self.pool. Now notice in this case that we are applying an average pool 2D, and therefore this particular implementation that we are having for a rest block will only work if we do a stride 2, or we are restricted to using a stride 2 in the convolution path. We will later on figure out how to get rid of this limitation. But for right now, if the stride is 2, then this will still work, because now we do an average pool 2D on this particular path. We have fixed the filter problem, but we have not fixed the size problem, and we are now fixing the stride problem. So if stride is 1 in both cases on the convolutional path, then again, there's no op, because we don't have to fix the shape or size, because that's the same in both the input path and the convolutional path. But if it is not, then we average pool 2D and we apply that. And finally, we define the activation. So what does the forward path look like for the rest block? For the rest block, we add the convolution of X, and the combination of IDCon of pool of X fixes the two situations we might have, which is Ni is not equal to NF, and the size is not equal to the size that we get from the convolution path. So applying IDCon of pool of X fixes these two problems, as we've seen here, and we add that to the convolution, and then the activation that we did not apply to the output of the convolution, is because we apply the activation to the addition of the two parts. So the two parts that converge here, the convolutional path and the direct input output path, we apply an activation to the output, and that then becomes our output of the REST block. So that's our definition of what a REST block is. One
where's
thing,
the
if you watch
activation applied?
Here.
Okay.
Here.
Oh, yeah.
So one of the things that you would, sorry, you have a question?
No, please continue.
Okay. One of the things, if you watch the video that he talks about, because if you look at the video code and then he is actually fixating this so you don't see it. But in the video, you'll see that he applies a batch norm and he kind of initializes the batch norm to values to be 0 initially, and then gradually as the network trains, it learns to kind of have actual values for batch norm. But they also found out that as they went through the course, they figured out that they had made a mistake or a bug in the sense that they weren't norming or applying the batch norm initially. And once they applied the batch norm or passed the batch norm as the norming function, then they found out that zeroing the batch norm actually gave them a worse performance than not zeroing it. The net effect, if you watch the video, is there's some things that he did as he was teaching the lessons that resulted in poorer performance, which meant that he just removed that logic. And the logic that eventually we are using is the logic that we talked about. There is no change in batch norm. If batch norm is applied, we use it. It turns out that if you look actually at the residual blocks implemented in payment stuff, they may do what he talks about of zeroing out the batch norm initially in the layers and then allowing it to, as it trains, acquire the batch norm values. But his point is that that might be working well for very deep residual networks. Since the residual networks that we are engaged in, I have only 4 or 5 layers, or at most 6 layers. That batch norming still applies batch norm, but the zeroing of batch norm initially doesn't seem to work as well. So that's what is something that you will kind of figure out is different in the code than what he's talking about as he teaches the lesson. But this is the code that eventually the result of all this discussion ends up to, let's not do anything with batch norm. It actually does provide us with a better result, at least for the depth of the network that we're talking about here. Now, remember that we modified the get model a little bit. So we now have a get model where we are going to 128. Remember that we started off with only up to 64. So there was only 1, 2, 3. Now we're going up to 128. And we are using the 128, the first step of the convolution, to be a stride 1, as I talked about just a few minutes back. So that's what our get model now looks like. But while we have added the REST block, let's do a couple of things to increase the depth even further. Okay, so we've gone from 8 to 128, but let's add one more layer and go from 128 to 256. So that means that, again, the 1 to 8 step, right, it will be a stride 1. And then after that, it's, the single convolution just applied. Actually, it's 2 convolution because it's the REST block, but bottom line is it's a stride 1. So the size doesn't change on the first set of convolution. And then we go 1, 2, 3, 4, and 5 convolution layers. There is 6 convolution because there's also a REST block when we go here, and each of the convolution is actually 2 convolutions. But all that said, we go from 1 to 8 with stride 1, and then we go from 8 all the way up to 256. And then we apply a stride 2, and the norm is batch norm 2D. The one other small change that he made is previously the 128 channels went to 10 channels. If you go back and look at the get model, you'll see the 128 was going to 10, and then so therefore we have a 128 going to 10, but we still have the 2 by 2, right? And so we then flatten it out in that case. But here, what we do is that we take one more convolution step. So when we take one more convolution step, the 2 by 2 output goes to a 1 by 1, right? Each time, because it's a stride 2, we have size. So if you work through that, you'll find that we are left with a 1 by 1 input. And working on a 1 by 1 input, that is, we'll get 256 1 by 1. And working on a 1 by 1 input and a convolution is identical to just a linear layer. So we can just, since the last two slice elements are 1 by 1, we can immediately flatten and then apply the linear layer going from, once we have flattened it, then we go from 256 to 10 with a bias of false and apply the batch norm to that. So those are the two small changes, and increase in the channels going from 128 to 256. And then in this case, because we have done that, we can get the final output to be a 1 by 1. So we kind of flip the order and we basically do a flattening here and then apply a linear layer. So that's the minor changes in addition to just changing the con block. If you go back and look at the nodes here, and it's really quite impressive in that sense. This was our previous get model, and it stopped at 128. And you see these as just the con block. We have just replaced exactly the same code with, instead of using the con block, we have just added the rest block. And as I mentioned, the only other change is we have kind of swapped this and made a flatten because we have added a one more layer, and as I explained, and then gone from linear output to and then applied the linear layer going from 2 to 6. Okay, one other thing he adds here is something so we can look, it's a print shape function, or that there's something function, which is just a hook. And we supply the typical things we need to supply for a hook, which is the model, the inputs and the output layers. And it prints the name of the layer as well as the input and the output shape. So this is a handy function that allows us to kind of look at every layer of our model. And you can see that the first one, because the batch size is 1024, single channel 28 by 28 going to 1024, 8 channels 28 by 28, and on and on and on. You can see what happens in the case I was blabbering about earlier, which is the 1024, 128 goes to 1024, 256, 1 by 1. When we added this additional layer, we caused the output to go from 2 by 2 to 1 by 1. So because this is 1 by 1, now we can just flatten. So that then goes to, that's what this is. We are just flattening it, getting rid of these two and make it 1024 to 256. Then we can apply a linear layer that goes from 1024 to 256 to 10, 1024 by 10. And then we also apply a batch norm to the output. And then he just batches a summary function, which is same as the print shape, except it prints it nicely in the format that we want. And we run a simple batch, single batch callback, and that allows us to literally print this neat total parameters that we have for every layer, the input, the output, what's the module name, and the number of parameters. The kind of key thing to note is the total number of elements or the total number of parameters in all our network is about 1.2 million. And you can see one of the things is that it's this final layers that have most of the parameters. The early layers have very little parameters, right? Because even though they are processing a significant sized image, significant in a relative sense. All of these images are small in a grander sense, but still we have 28 by 28 images going to each channel 28 by 28, but the number of parameters is fairly small. And here, because we have a 1024, 64 channels, 128 channels, and 256 channels, you can see the number of parameters being about of the total 1.2 million, about close to a million or 900,000 of the parameters are in this layer, and about another 230,000 are in this layer. So these two layers contribute the most of the parameters, right? So as an aside, you can kind of print them to see where you're getting and why you're seeing these parameters to be as high, because in this case, for example, you have 256 3x3 channels, and that's the, if you print this out and look at all of the parameter counts and so on, you can see that the values here and here are what contributes to this significantly high number of parameters in these two layers. Okay. Now, back to just trying to determine the LR, and he has already patched the LR find on to our learners. So you kind of look at that and you go, okay, I can use in this, it's about 2 times 2e minus neg 2, and choose that LR, everything else the same, learn.fit. Now, remember that before we started this exercise, we were at about 90.6. Let's look at when we made it deeper, and where did we get to? We already have improved it quite a bit, about 10% reduction, because we started off, as I keep saying, at 90.6. We are now at 91.8 with just a simple deepening of the layers and widening. That is adding one more layer and increasing the number of channels. But then we are doing that again, and also we're going from 128 to 256, and we're using REST blocks rather than the convolutional blocks. So we will see in a minute what that enables us to get to as we train. But as we do that, while it trains, let's also kind of keep pushing forward. One of the things that he points out is, if he then said, okay, this network that we created is a very simple network. We created this net block, just converted convolutional to ResNet, just increased to 128 to 256. Kind of very simple things we tried. But why don't we try from Tim, which is the Ross Whiteman. Now I think it's all on Hugging Face, his models, but if you look at the whole Tim library, there's all kinds of residual networks. In fact, if you just list all the models that say ResNet star, here's the extent to which you see the different models that we see in a minute while it finishes training. But the bottom line is, hey, it encourages us to kind of look at all the code. It's very neatly laid out, and it's all modularized, so you can kind of figure out all the different variations of ResNet and how those variations are applied to the code. The bottom line is, he played around with a bunch of these ResNets that you'll see in a minute. You can see how many they are. And you can also see with ResNet how far we've gotten. Remember, we started at 90.6. When we converted to resolution ResNet blocks, we have gained another, we were at, I think, 91 something. We've gone to 92.8 in terms of our performance. And all this, keep in mind, is only with 5 epochs. Okay. So that's where we are at 92.8 with our own handcrafted, very simple ResNet blocks. Here is the vast number of ResNets with all the variations possible. And he says that he played around with a number of them. And the one that he found that gave really good results for the fashion MNIST data sets, at least, is the ResNet 18B model. pre-built, pre-trained using this TIM library, and he trains that, and let's kind of figure out what the comparison results in. Remember, the comparison we are trying to do is with our own output, which is around 92.8. Okay, so while that trains and finishes, we'll kind of move to the next notebook. So remember, what we've done in this is essentially just converted our convolution network to a residual network, kind of understand the purpose behind a residual network, and try to get what our output and performance of the residual block based ResNet for fashion MNIST classification. And keep in mind, because we'll be making many more changes and trying to get to the state-of-the-art performance, keep in mind that a very basic ResNet with just an addition of a layer and a few minor mods has gotten us to about 92.8 in terms of performance. And you can see when it finished that the best that he could find, even using a TIM, not anything else fancy, but just a ResNet-based architecture, which is about 92.4. So it's in some ways quite impressive that with hand-coded but carefully crafted, initialized, well-initialized network gets us a very comparable performance. In fact, it beats the performance of what is pre-trained network, at least for fashion MNIST, picked from all of these variety of ResNets that already exist in the library. Okay, so that's what this notebook is. Now we switch to the next, which eventually will lead us to augmentation and other techniques, but let's I won't be running this notebook because it takes a very, very long time to run, as you will see in a minute as we go through the notebook, because there are cases where we train the network over 20 epochs and then over 50 epochs. So we don't want to sit here and wait while the network runs, but I'll just take you, I just managed to run it to completion yesterday. So I'll just take you through the various results and discuss the changes that he makes. So the setup for all this is very similar to what we have before. We download the stuff, get the the typical kinds of callbacks. We just standardly using 5 epochs. We are using 6E-NEC2 instead of 1E-NEC2. And if you go back and look at the LR find plot, we'll find that that's still pretty reasonable value to use. You're still at the slope, steep part of the downward slope. The first step, he says, is let's see whether we can improve the model even further, right? So we've seen that the residual networks, one of the things, if you read the paper on residual networks, they fix the problem of training deep networks. So residual networks train as good, if not better, than the traditional convolutional network. So if they do that, if their training is indeed better, then there's no reason we should stop at 256. So let's take one more step and take it to 512. Right? If we are doing that, then if you're doing that, meaning if you're increasing the depth from 256 to 512, then one of the things we may want to do is remember that until now, we were going the first convolutional step, which was a stride 1 step, we were taking from the input channel, which is a single channel image, because this is fashion MNIST, and so it's just a black and white image. So input channel is 1. So we were taking from 1 to 8, and then we were going from 8 to 16 to 32 to 64 to 128. And then in the last step, we added 256. Now we're adding one more to 512. So one of the things we could do is, instead of going from 1 to 8, we could go from 1 to 16. But if we want to go from a single channel to a 16 channel output, then we also should think about the filtering we are doing, because the filter is a 3 by 3 filter, right? So 3 by 3 filter has a 9 inputs. So we're going from 9 inputs to 8 inputs. Now, if we kept it the same when we go from 1 to 16, then we are actually not learning as much, right? Because we'll have only 9 inputs going to 25 outputs. Because remember that, 9 inputs going to 16 outputs. Now, what would be better, on the other hand, is going from 25 inputs to 16 outputs, because at least then we will be having the ability to learn, right? Just like we had before when we went from 1 to 8, but our channel or the kernel size was 3 by 3. In the 3 by 3 kernel size worked when we went from 1 to 8, because we had the input was 3 by 3, which meant it was 9 inputs going to 8 inputs. If we retain that, that would become 9 inputs going to 16 outputs, in which case we are not learning as much, right? We'll be duplicating stuff. So because of that, and because of that realization, and this is where, for example, thinking through why we do certain things and what are the number of inputs and whether there is learning happening, and when we change these values, is kind of an important tips and tools and tricks that you learn as you go through the course. So in this case, he says, okay, we can go from 1 to 16, but in order to, and we do that in order to increase the depth here from 256 to 512. But when we do that, let's be careful to change the kernel size from 3 by 3 to 5 by 5. So in this case, he has added an additional layer which takes us from 256 to 512, but also changed the kernel size to be 5 for the first layer. Everything else remains the same as before. Now, we define the new get model, apply these, and we fit, and we see, remember, we were at around, the last thing we did with our approach was 92.8. Now, compared to 92.8, let's see where we end up with these changes. Still keep bumping it up. From 92.8, we are now at 93.2. So that gives us another 0.4 increase in our accuracy. Again, everything keeping the epochs just to be 5. Okay, so remember.
For the stride part, for the next layers, they have, he has put it as 2, the stride. For the next part, I think so here, yeah, as you can see in the third line. So I was not sure why he has done this stride as 2 here.
Well, that's the standard stride that we apply, because in any of these changes, we obviously shrink the image by 2x as we go through. So that's typical. That's nothing new.
Okay.
That's, this stride is what is important, because we don't change it going from 1 to 16. But then every one of these steps, we obviously want it to go reduce it by or half the size of the image. So this is typical. Nothing new.
Okay, so the stride has to as just to reduce the number of channels. Increase the number of channels.
The stride doesn't increase the channels in any way. The stride changes the shape.
Yes.
Image. So it halves the image size. It goes from 28 by 28 in here to 14 by 14, 7 by 7, 2 by 4 by 4, 2 by 2, 1 by 1, then flatten.
Okay.
You can go through the math, but that's what happens. So this is normal, thing new there. It's just typically we are probably used to saying stride equals stride, but stride eventually is 2 for everything except the first layer. And again, keep in mind that every rest block what happens is this stride becomes 1 for each rest block, the first one, and then it's 2 for every other. The second of the convolution is where the stride change happens.
Mm-hmm.
So, but with all that said, we are now at 93.2. We do this. We started at 90.6. After changing to resolution, ResNet, we update. Then again, we update when we increase the depth. We have now increased the depth some more, and we are now at 93.2. Now, if you recall, I had said that our initial implementation of the REST block had this one flaw where we eventually had to get to 2 by 2. And if we didn't, then we'll run into a problem because the 2 by 2 was where we did the average pool 2D. The average pool 2D only applies if our eventual output that we're providing as input to that is a 2 by 2 sized value. We don't want that to be an ongoing limitation. So that's a limitation or a lack of flexibility, that our number of stride 2 layers has to be just so exact that we end up with a 2 by 2 so we can apply an average pool 2D. And that's not something that, obviously we can't count on it. And that means that we'll have to exactly count how many layers we take that model through and so on and so forth. And that's what I've explained here. But one of the ways to get rid of that problem is to do something called a global average pool. That's the name in terms of the TensorFlow, but it's actually called adaptive average pooling in PyTorch. But it seems that the adaptive average pooling in PyTorch can have it. One of the things is it can output something different than a 1 by 1. So he kind of, to avoid all that confusion, he just defines the equivalent of a global average pool in PyTorch and uses that definition. The definition basically says take the mean across the last 2 dimensions, which happen to be the height and width. So that's what a global average pool does. And now we just replace the keeping the 2 by 2 dim that we get when we come up to this level. And we just, when we go from 256 to 512, which is the last of these layers, then we just do a global average pool. And once we have done a global average pool, we are now at the 1 by 1, and the 1 by 1 also disappears because we have the average pool across the last 2 dimensions as shown here. And now we can directly apply a 512 to 10 linear, right? There's no need to flatten.
There's no need for flatten here.
Yeah, there is no need, right? Because we have just averaged over the last 2 dimensions, so they disappear. So you just get the 512 output. So if you print out, as we'll see in a minute, you will see that it's gone. The 1 by 1 is gone. The flatten was just done to remove that 1 by 1. And we have removed it by doing the global average pool across those 2 layers. And then the 51210, bias false, batch norm it, and then this. So this is our new definition of get model, which is our get model 2. He defines, earlier in the last notebook, we saw the print whatever function. Here he adds to that the flops count. Now, being an ex-hardware guy myself, I'll continue to repeat something a few times as we go through the rest of this lecture. Is first of all, the thing I would say is here he is not so much really counting the flops as he is counting the number of multiplications that are done. That's point 1. The second, but he calls it flops, and typically people call it flops. So that's one thing you need to realize is it's not actual count of floating point operations as much, or all floating point operations, but just the multiplication operations. That's point 1. The second point I would make, which is even more important, is and it's been proven even in recent papers by Google, is the following. The only actual true measure of performance in any system is the time that an algorithm takes to run. Flops, matrix multiplication counts, any other counts is a proxy, and as with all proxies, they tend to give erroneous results. And if you pick up the best hardware book on computer architecture, which is the NSE Comparison book, the first thing they tell you is don't believe anything other than time as a metric of performance. And it's hilarious because even DeepMind in Google or Google Brain published a paper which said, oh, look, we have this great technique where, I forget the name of the technique, but they were doing some segmentation. And they said, okay, you can do a layer-wise, or we call it some other, I forget the technical term they used for not doing convolution across all the channels. And they said, look, this gives us, really good, and look at all the improvements we're getting because of the flop count reduction. And as I said, matrix multiplication. So if you're not multiplying across all the channels, then obviously you're getting a reduction in the flop count or the matmul count. And they published the entire paper. 6 months, 9 months later, they published yet another paper, and I thought this was the most funny thing that that happened. And said, oh wait, when we actually ran the paper and figured out the time that it took, it actually took longer, because when you don't multiply by all the channels, you're not fully utilizing the GPU parallelization, and so we actually get worse results. So now we have fixed that problem by doing these 2 or 3 additional things and really get the benefit. So the first paper was published saying, oh, look, we get better performance. How? Because we count the flops. And then the second paper was published saying, well, we don't actually get better performance. We get poorer performance when we run it on GPUs. Well, what else would you run these kinds of networks on? But when we actually fix it, then the issues, because flop count is not a good metric of performance, then we really get good performance on GPUs. So, given that my background in hardware is important to one, and however, all that said, if you're comparing apples to apples and the same kind of networks and, have enough set of caveats, it's okay to measure flops as approximate proxy, but you always have to be careful about counting them as a measure of your performance. I'll never believe flops as an indication, always be suspicious of them. But nevertheless, you will see a lot of papers, especially in machine learning, which continue to count flops and indicate them as a proxy for performance. In this case, what he does is he just says, if I have a dimension less than 3, then I'm assuming that it's a linear layer. So I just count the number of elements in it. And if it's 4, then I'm going to assume that I have a height and a width. So it's not just a number of elements, but the number of elements multiplied by the height and width, which would be the number of multiplications that I need to do. So that's just a commentary about that. And otherwise, just the count of flops. So if you run that through the single batch and then publish the summary, which is the patched version, you can see that the last column has been added. And you can see again that the number of parameters is most significant in the last 2. We saw this part already, but you can see the last part where it goes from 512 2 by 2. Right, and you can also see the thing that once you average pool over a 2 by 2, the 2 by 2 goes away, and therefore there's no need to flatten. You just get a 124 by 512, and then you can go linearly from 512 to 10. So you can see that these 3 layers have most of the parameters, and in fact, most flops, which is most matmuls, happen in this layer because you're going from 256 to 512 with a 2 by 2. Right. Now, the other interesting thing, let's then train with this, and we see we are at 93, about 93, right, is what we ended up at. Now, where were we? We are at 93.2, so slightly better even here compared to adding even another 512 or doing the average score. But, you know, 0.2, about the same, one could say. The question then he asks himself is, okay, we did this and we increased the number of, now look at the number of parameters. We went from 1.2 million to about 4.9 million. So keep in mind that we didn't get, actually we dropped a little bit, but if we squint, let's say that they have approximately identical performance, but then we have increased the number of flops. Well, we didn't count the number of flops earlier, but the number of flops now is 33, but the number of parameters is 4.9 versus 1.2. So the question becomes, can we get about the same level of performance, but using, say, less number of parameters, thereby speeding up our network? So he tries a couple of things. Let's say we remove the code that takes it from 256 to 512. Why is that helpful? It's helpful because of what we see here, right? That's the one that contributes most of the increase, about 3 million parameters, if you will, of the 4.9 and about 14.7 MATML or flop count, right? So you remove this, and you can see that there's a huge reduction in the parameters, right? And the flop count, we'll see in a minute, also is reduced. So you get model 3, you drop the 256 to 512, you keep the 1 to 16 with a kernel size of 5, do everything else the same, and see where you get to. And of course, you'll immediately see a drastic reduction. And you also see a megaflops reduction from 33.3 to 18.3. Now, what's interesting, if you look at the megaflop count or the multiplication count more accurately, is that the difference here is not that much between the first layer and this layer here. In fact, the first layer gives you a more, or I should say a higher flop count. Why is that? That's because in the first layer, even though you're just going from 1 to 16 channels, you're doing it over a larger height and width. That's the reason why it's important when it's, you know, channels as well as height and width to do this part. So even though your number of elements may be comparable, you have a large height and width in the initial portion of your network. You have this to be 28 by 28. Whereas towards the end of your network or deeper into your network, this is a 1 by 1 or a 2 by 2. So if the number of elements remains approximately the same, then these two factors have a significant impact on your total count. So that's what happens in this case, right? And remember that when you're going from 1 to 16, you have two convolutions in a rest block, right? The first convolution takes you from 1 to 16. The second convolution takes you from 16 to 16. Now, the second convolution is the 16 to 16, and you have a 5 by 5. So in effect, a large portion of the MATML count or the megaflop count comes from the second convol of a 16 by 16 by 5 by 5. So that's a significant chunk that your 5.3 megaflops count comes from, right? So he does it in two steps. First, he says, let's just train this and see where we get to. And we are about at 93.0. So it's about the same. It doesn't dropping from 4 point something down to this guy, right? And this is just an explanation, if you will, of what I just went through. That is, the first of the two convolution in a rest block is a 16 by 1 by 5 by 5. The next is a 16 by 16 by 5 by 5. And that's where most of the MATML for the 5.3 megaflop count comes from. So you do this and they drop by about 0.2. So it's not terrible. So even though we've gone from a 4 million parameter, 33.3 multiplier count, megaflop count to a 1.2 million parameter, 18.3 megaflop count network, we have not actually dropped significantly in performance. We are still hovering close to 93. We're at 92.8, right? The question is, can we make it even faster and see what the impact on performance is? As I just explained to you, the second convol is where most of the multiplication count comes from for our first channel. So what if we didn't use a rest block, which is this two convolution, and instead just drop the second con or drop the rest block and converted it to a traditional con block. So that's what a get model 4 does. It takes the first layer and instead of having a rest block and having two convolution, it just does a convolve, our traditional con block, 1 by 16 in case of y. Otherwise, we keep the rest of it to be the same, right? And this is my warning that, again, be wary of comparing megaflops as an indicator of performance. But because here we are keeping everything else the same, the network is the same, we're just changing a few parameters, we could potentially say that, and we're keeping the underlying hardware the same, so it's okay to kind of say that the megaflop count could be a metric of or a proxy for performance. And we do that and we train, we look at the megaflop count, look at how small our first layer count is. And we have dropped from 18 to 13. So we have dropped by about 5 million multiplications, floating point operations. The total parameter count doesn't change drastically because these two still remain the largest contributor. We've just gotten rid of the 250 change. And then we do the training and we're a little bit lower. We used to be at 92.8, we're at 92.6. Again, a 0.2 change, for the significantly lower count and a faster evaluating network is still not a terrible trade-off. So we're kind of hovering about the same, maybe dropping a little bit by about 0.2 or 0.4. The question then becomes, can we regain by other techniques that 0.2 or 0.4 loss that we are seeing while keeping the speed and the benefits we get from a simpler network, faster network? So the question is, so far we have been only training with 5 epochs. Obviously, if we train for longer, then we could get better. That's trick we have not yet pulled because we wanted to do everything else to the network, get that network in the best shape we possibly can through our thinking processes in a brain cells, and then use the best. And then after that, kind of resort to doing the simple thing of just giving it more compute horsepower and see where we get to. And we see his point is he tried 20 epochs instead of 5 epochs. And while the test accuracy goes up to 99.9%, we anticipated because we have increased it to 20 epochs, but the test accuracy is about 92.4, and that's about where we are even now. So while we have maybe increased it by a fraction from 92.6 to 92.4, or in fact, in our case, we are actually getting it better here. So maybe if we ran for 20 epochs with this, we may get a little bit even better. But be that as it may, the point he's making is we don't really get too much better performance as we increase the number of epochs. Now, the question is, why is that? And one of the issues he points out, which I must admit is something that it is interesting to think about. And that's the thing I appreciate about the course, is it also makes you think about all these little tiny details and understand them a whole lot better, their interactions, if you will, as well, because we tend to, otherwise, when we're dealing with much larger networks, much bigger problems, we tend to kind of sweep these kinds of issues under the rug, so to speak, is that his commentary about Well, when we use batch norm, then weight decay does not really help us with regularization. Why is that? And he kind of goes into that a little bit in the lecture, but the bottom line is this, right? If you think about what batch norm does, it kind of, as we have discussed before, reduces the focus of the network, quote unquote, my words, into this multiplication addition thing or a couple of parameters, the mult and the add, right? And that, as I've talked about in previous lectures when we discussed batch norm. So if that's the set, that's the single set of coefficients that are referred to here, which multiplies the layer. Now, the batch norm itself doesn't have a number of parameters, right? It just kind of eventually reduces or brings down the parameters to this mult and add values that it learns. What it does, though, is it multiplies the convolutional weight matrix by the mult and by the and then adds the add, right? So from a weight decay perspective, batch norm doesn't have too many weights that it contributes, but it blows up or increases the significance of the weights within each of the layers by just multiplying them by some value and adding some value to them. So in effect, what batch norm does is it kind of helps the network cheat by giving it these two parameters that it can control and increase the weights. But by doing this, it minimizes or it actually completely negates, depending on the network, the weight decay. So weight decay, when you apply it where batch norm is used, tends to not help us as much in regularization. People still apply weight decay apparently because it has some second order effects, but the second order effects are not what we are actually looking for. We are actually looking for an impact on the weights and the reduction of the weight, which is nullified by batch norm. So that is a long way of saying that we need to also do other things in order to improve our generalization performance. So then we get into, okay, how best do we do or improve the generalization of the network if we are not to rely on weight decay because we have used batch norm and they get into contract and it doesn't help us a whole lot. So we go down the path of applying augmentation, and that means we change the images that are going in as input in order for the network to be able to handle its classification performance and retain its performance while seeing images which are not exactly the same, but modified slightly so that its performance under test conditions is better and it's able to generalize better. So we define a transform function for the X and the Y, define them to be no ops, and we return the transformed 0 with B0 or batch 0 index, which is the image, and the batch 1, which is the label. The labels don't need to be transformed in this case, so the labels, there'll be no transform Y, which will continue to be a no op. In the transform X, we apply two transforms. One is a random crop. Now, cropping a 28 by 28 image and cropping it further will randomly result in a different size. And so in order to prevent that, what we do is we pad the 28 by 28 image to make it 32 by 32 and then take a 28 by 28 image chunk out of it. So we don't change the input size going in. And then we also do a random horizontal split. So those are just the simple two transforms. And this part is where he violates one of the tenets he had used in the course because, as he says, many of these transformation code is very simple. There's not much to learn about in this, so I'm just going to continue to use them directly from TWIML. And of course, if you want to go into details of how those are done, FastAI does a lot of these. And then there are also, I think, augmentation. I forget, there's like an excellent augmentation library that has. That's what most people use in Kaggle and stuff. So you apply the transform, you define an augmentation callback, which is batch transform with a partial, where you just apply the X transform in our case. And then he added something to the batch transforms, which says, do you run it on training on val? And the default is both of them true, that is, you turn in the both. But in this case, we do not apply the augmentation and the validation condition. So it says on val is false and on train is always true. So as I said, this just defines that the transform batch, which means apply the transform X to the transforms. In our case, that is just apply these two transforms to the image. Define the learner, pass it through fit function single. And if you define a single batch callback, then by doing all this, what we are doing is just passing a single batch through so that we can plot the image after it has been transformed in this way. And so we can see exactly what are the set of inputs going into our network after they have been transformed. So this is what they look like. And you can see that they have been flipped. And because of this, addition of 4x4 and then a patch or a crop, you can randomly crop, you can see these things. He also mentions that one of the things is when you apply a crop or a transform like this, the entire batch is identically transformed. Now you could argue that even better thing to do would be to apply a particular transform for each of the image. But as he mentioned, because there are about 15 and 60 mini batches that we run through, that's not really necessary because each of the mini batches will obviously choose, will have a different set or a slightly different cropping and so on that will get applied. This is just patching of the show image batch. And so you can see after you can plot again the learn show image batch for another batch and see what happens in that case. So you apply the transform, define the augmentation callback, go through 20. Now, of course, we have base network to be strong, and we have kind of applied the augmentation. We now increase the number of epochs on which we do the training to 20 epochs. So this is where, the reason I didn't want to kind of run the notebook per se, because it would take a long time to do this. And now we see that instead of hovering around 92 point something or around 93, we have nicely moved up to 94%. So 94% may seem to be still not that great, but keep in mind that if we look at the image classification on Fashion MNIST, and again, also keep in mind, we have handcrafted the network. We have learned every line of code that we have used in generating these networks that we're using. And we are only training for 20 epochs. And we are at 94.4. So we are in the top 10 of the state-of-the-art results. And most of these results have been published in 2021 or 2017. These guys were really pretty good, but we'll get to that as well in a minute. But we are in the top 10 of results with only 20 epochs. And if I recall correctly, most of these papers use a ton more epochs in their calculation. So it is, in fact, a remarkable achievement that we are at the state of the art with 20 epochs, handcrafted network, every line of code that we have built ourselves, and with Fashion MNIST, right? And nothing fancy. None of these, dense nets or Inception, because this one seems to be VGG, but we are as good as at the top with just 20 epochs and getting a fantastic accuracy. So that, in a sense, tells us that if we are thoughtful, if we are methodical, and use just the simple techniques but pay attention to the details, we can do what some of the state-of-the-art papers have done with in this code. As I said, now that we are training for more than 20 epochs and so on, let's kind of save the model. Now that we have applied augmentation to the training, we can also potentially do something a little more kind of interesting or fun, and that is to say, apply augmentation not just during training, but apply augmentation to the models during test and see whether that gets us even better results. For that, it defines capture predictions. That means, as a callback. So defines 3 different sets of things that he wants to capture: inputs, the predictions, and the targets. And after the batch, he captures the single output of the batch, the predictions, and the labels and the inputs. And then after fit, and actually just moves them to the CPU so you can kind of plot them, if you will. And after fit, he just cats means, he just stacks the predictions, targets, and inputs, patches the capture preds onto the learner. And by applying learn.capture preds, he captures the predictions and the targets. And by running just a single batch through it, you are able to see that the accuracy is 0.94, right? This is for something that we have done already. He just runs it through the callback. The callback don't do anything other than repeat, just captures the predictions and says that accuracy is 0.94. The thing here is then you can apply test time augmentation callback to the batch transform callback. Add the simple, now, unlike the random crop, which is done in addition to the horizontal flip, for the test time augmentation, we just want to do the horizontal flip. So that's the only transformation we do on the X, that is for the image, is a horizontal flip. And unlike previous case of train augmentation, here we want to do it on validation. So we say on val is true. Right? So test time augmentation, and then we do the callbacks, and we find out that when we do test time augmentation and capture the accuracy, we see it increasing slightly from 0.940 to 0.941. And now one of the things that he does, and I've kind of just broken it up so that I can kind of look at the details. These are my additions to the code. You stack AP1 and AP2 and take the mean. That's the average prediction. And that's basically what he's doing here is ensembling the test time augmented model and the non-test time augmented model. So he just averages them and uses that as the result. This is something we should be all familiar with when we have done much on Kaggle. So it's just basically an ensemble. So it's an ensemble shape is 2 by 10,000 by 10, because 10,000 is the number of validation images. And then if you take the mean across the 0 axis, which is ensemble mean 0, you'll find that you will get that, and that if you use the argmax, that and round the 2 to 3 decimal points, then you find that by ensembling the two, remember one was 0.941, the other was 0.940, but by ensembling the two, you're able to get a performance of about 0.943. So that's kind of what I think would be the best performance, but there's a couple of tricks up its sleeve still to see whether the performance can be improved even further beyond this. This is something I wanted to do. I haven't had time to do it, but for those of you kind of were participating in this VS competition, there was this thing called stochastic weight averaging, which essentially does the following: that even when you're actually just running a single network and a single set of weights, what it does, the stochastic weight averaging, and it actually is in PyTorch, but I wanted to, as he has done, code it myself as a callback, implement it, and then see whether I get identical results to using the PyTorch version of the stochastic weight averaging. Stochastic weight averaging, what it does is it just takes the last couple of models. Now, as you go through, even on a single model, it's obviously adjusting the weights, right? So all along the path. So what stochastic weight averaging does is it takes the last, you can choose how many ever number of models that you want to retain, the weights of, and it takes the average of those last three instead of just giving you the best one. And that's another way, if you will, of ensembling the weights. So I just wanted, this is something that if you have the time and the interest, this would be something interesting to buy, is to code stochastic weight averaging callback using his techniques, and then use the PyTorch version of it and see whether the best results and see whether you can beat the score that he has, which is 94.3 at this point. Couple of other things that he tries is random arrays and random copy. And let's quickly go through and see whether they help us and also understand what these techniques are. So random arrays just says that what I'm going to do is I'm going to randomly erase some portions of my image, thereby making it like a augmentation, if you will, and then see whether my network continues to perform as good. So it's a form of regularization, if you will. But when you do that, you have to be careful that you're not changing the actual data distribution of the input images. The underlying data distribution is not something that you should screw up. So calculate the mean and the standard deviation, in order to kind of figure out what they are. And then let's say you want 20% of the height and width to be erased. So you determine where, so you have size X, size Y, and where you want to actually change the, and the size of the, and the location of where you want to change the stuff. And let's say you do normal initialization of the mini batch. That means that everything in the batch, that's the first value here, all the channels, and then you take the X and the Y, which is the height and the width, and then determine the slices, and you want the mean and the standard deviation to be what you've already calculated, right? And then you show the image. So you can see that these are the chunks that you're randomly trying to erase, right? But what he found is that the original distribution of the images is not normal. So when you do this to be normal, you're not actually kind of keeping the staying true to the distribution. So even though you are adhering to trying to keep the mean and the standard deviation the same, what you unfortunately are altering is the range of values in the input. So he then had to clamp the ranges as well to be consistent with what the range of the original images are. He just defines a random arrays function so that you can define how you instead of this single lines of code, define a function to do that. And then subsequently plot it, but also not only define and then check the mean and the standard deviation and the max and the min and the max. But not only do you want to randomly erase, but you also can give it a parameter saying how many random erasures I want in my image. So you can say, okay, I want a 20% erasure, but of 4 blocks. Okay. So that's another thing that you can provide to the rand arrays function. Plot that and define it as a class, transform it, do a rand arrays as part of the transformation, and then train based on that and fit and see a plot. You can see because there are 4 of them, you can see 4 of them in the plot. There are 4, depending on the randomly pick and choose and erase. And now he trains that for 50 epochs doing random arrays. And when you do the rand arrays, you get even better, 94.9. Remember, we were at about 94.3. It was the best when we ensembled the test and augmented callback based values, but now we are at 94.9. The thing that he points out is in random arrays, after a lot of effort, he still figures out that the mean and standard deviation aren't quite the same. He also has to kind of arbitrarily clamp the range. So he says, well, I'm going through a lot of kind of loops, if you will, to maintain all this inherent distribution. Instead of that, why do I erase? Let me copy images randomly from piece to piece. Move, it's kind of a way of saying you just kind of copy pieces of the image, but relocate them, if you will. And that then helps us maintain the distribution a lot simpler, right? Because you're just shuffling, if you will, the location. That shouldn't cause any distribution changes because the underlying mean and standard deviation, if you're just copying, should remain the same. So he kind of gives up on the erase part and instead implements the random copy. The rest of it, the logic should largely be similar, right? Because you're just copying portions of the image. So you can see that, chunks are missing and they just get copied over into other places in the image. Define the class, do the plotting, define how many copies you want to generate randomly, that you want to copy from portion to portion, plot them so you can see, copying is being done, and again run it. 25 epochs in this case, and the rand copy gives us 94.4. So the rand arrays gave 94.9, rand copy is 94.4, but keep in mind that rand arrays was one at 50, here at 20 or 25, we are still at 94. So bottom line, these two techniques still seem to give you a little bit of a boost. And by the time we are at 94.4 and 94.9, remember we are better, or 94.9 is definitely better. We are in about the 6th spot at only 25 or 50 epochs. That is a pretty impressive accomplishment. And then he does, let's see, I think, learn to, and he gets 94.3. I think he just runs it twice, maybe once with test time augmentation. Maybe just runs it twice. And again, averages the two, 94.3, and you do the rounding, and you're at 94.7, basically by ensembling. So you can see that we have beaten the 94.4. We're at 94.79, something in that range, by using the rand copy, rand arrays kind of techniques in addition to the augmentation. And again, we haven't used test and augmentation here. You could potentially do rand copy and then apply also test and augmentation, just a horizontal flip, and see what that does and see whether that gets you even better. And in fact, if you looked at when he was teaching the course, he kind of went out and said, hey, are there people who can beat me at 5 epoch, 20 epoch, and 50 epoch? I haven't checked that particular thing. Here is the challenge as to what, and you can see that people have bested this result that he got. And at 20 epoch, the best is 95.7. 50 epochs, 95.8, and at 5 epochs, 94.9. At 5 epochs, 94.9 is pretty amazing, given that 94.9 is better than the 5th place result. So you'll be in the top 5 or 6 at just 5 epochs. So that's really a pretty interesting result, not because the data set is challenging, but because the techniques that have been applied are very simple. Every line of let's see. Can you hear me?
Yeah, we can.
Okay. Then the last bit, and I'll cover it here, even though he covers it in the next lecture, but it kind of will help us in the next lecture, because next lecture on, we're going to start spending time on much more complicated stuff, which is actual stable diffusion code and stable diffusion algorithms and stuff. So that will entail quite a bit of kind of theory as well as application.
We can't see
Here,
your
he just
screen.
points out, let me share. I think it disconnected the network for some. You should be able to see it now.
Mm-hmm.
Okay, so the last thing he does is also talks about dropout. Dropout, he just, again, as always, implements dropout himself and then uses the Python dropout going forward. So he says, let's take a distribution, a binomial distribution, and the binomial distribution with a probability of 1 minus p. So if p is 0.1, then the probability that you give to the distribution is 0.9. And in fact, funnily enough, it turns out, you just got the distribution sample, define a dropout class. The bottom line, if it's not training, then you don't do anything. If it is training, then take a binomial distribution and then move it to this with a probability of 1 minus self.p, which is 0.1. So it will be a 0.9 distribution. And you just multiply the x, which is your input, by the distribution sample and the size of x. And obviously, this is important to remember. Because during training, we reduce the number of, we randomly zero out a certain fraction of the inputs. We have to scale it back so that the size of the output doesn't change because we have applied dropout. But this is just our code to illustrate that we can understand what's going on in dropout. In effect, when we use dropout, we just do nn.dropout. And if it's a 2D network, we just pass it the value of drop, which is the percentage that we want of dropout. And then you use a drop model, and he trains that and ends up at about this epochs. Yeah, 5 epochs, and you're at 93.0, which is pretty much where we ended up with our 5 epochs previously as well. So it's with dropout, we kind of get as good as well. And then one of the things he talks about is, you can also have a callback where you apply dropout at test time. This is typically not done, but it's done in terms of some medical applications where you can actually use it to determine the kind of, what's that thing, probability called the error bars and stuff. But that's something he plays with, not important to the rest of it. Bottom line, this is just what's the understanding of dropout, which is randomly drop a certain number of activations in the layers, and if you can think of it as a form of regularization or a form to help us generalize better, especially in deep networks. The augment tool, let me just talk about this for a minute, because this will become much more important as we go through the rest of the classes, and especially when we talk about the stable diffusion. So far, the input that we have seen have been, if you go back and look at it, and I've been meaning to do it, I haven't gotten around to it, but it should be fairly simple for any of you to try. If you go back and look at our input values in fashion MNIST, they go from 0 to 1, right? Now, what this particular operation does is, and you can do the math and show this yourself, I'd encourage you to try it and work it through so you can convince yourself that's what this is doing. You take a tensor O and you multiply by 2. So that means you take 0 and you multiply by 2. That will be 0. And then you take minus 1 and you subtract 1 from it. So the 0 value will result in minus 1. Then this 1 value of O is, this is, tensor O, if its value is 1, multiply by 2, it's 2, subtract 1 is 1. So what this particular function does is it takes all of the values of the input, any tensor, and usually if the tensor values are, and that's the case he claims for all fashion MNIST input data, it lies between 0 and 1. But if you translate it to lying between minus 1 to 1, then you tend to get or see a little better results, right? And in a sense, you'll kind of figure out that this matters, the scale of your input matters, and we'll understand why more when we look at stable diffusion. But in stable diffusion, also the scale of your input seems to matter. The scale meaning the range and the set of values that your input values of pixel images or input values of pixels for your images lies between. And in our case, we are transferring something that lies between 0 and 1 to lie between minus 1 to 1. We aren't changing the underlying distribution, we're just shifting it to be about 0 rather than it being between 0 and 1. And then training it, and you can see instead of 93.0, we actually get 93.8. And that's the model we save as dataawk2.pickle. And that is the model that we'll use subsequently in one of our future notebooks. While he comes back and does this in one of the future videos of the lecture, I've kind of chosen to cover it because it's material right now, since we're covering the course much after his initial set of lectures are done. But it's important to understand that it's always interesting to figure out what are the range of your values, where does it lie, and thus, making it kind of be distributed around 0, does that help in our, in this case, it definitely does. And it also turns out to be material to the discussion. We go through stable diffusion. So that's what this augment2 does. It basically shifts the underlying data of our fashion MNIST, which happens to lie between 0 and 1, to lie between kind of symmetric values of minus 1 to 1 by doing this tensor times 2 and then subtract 1 during the transformation part of our input data transformations. That pretty much completes what these two notebooks do. And any questions? And this kind of completes, if you will, all of the infrastructure work that he takes us through, and all the lectures moving forward from here are all focused on stable diffusion and implementing the various papers and illustrating the uses of mini AI in so many different, and how flexible the framework is when we use it for a variety of implementation of papers associated with stable diffusion and also associated with many other techniques. Any questions?
No.
Okay, if not, see you folks later and Kaggle.
Yep.
Next week on, we'll start with stable diffusion implementations.
Thank you.